Hi, welcome to the second video on logic. This video is going to be focusing on truth tables. And in going through that, we're going to be skipping back and forth between the textbook that you can see on your screen right now, and in particular, we're going to be covering 3.1, this section on truth tables, and skipping between that and the online notes, and I'm going to work out a couple of examples for you. Now, while learning about truth tables, we're going to spend some more time talking about all those different logical operators and look at how we can examine them in Python. Starting off, we're going to look at negation, which you'll recall is just turning a proposition into its negative. So if we have a proposition P, not P is, it is not the case that P. So this is what is called the truth table for the negation of P. So a truth table means we have our basic propositions. In this case, we just have one, which is P, and we list all the possible combinations of true and false. Well, P can either be true or P can be false. If P is true, then its negation is false. And that's easy to see. If I say, you are a student at Georgia Gwinnett College. Well, if you're a student at Georgia Gwinnett, that is a true statement. That's a true proposition. So the negation of that, you are not a student at Georgia Gwinnett College, would be false. So you start out with a true proposition, its negation is false. You start out with a false proposition, you are from the planet Mars. Well, then its negation, you are not from the planet Mars, is true. So negation basically is like flipping a switch. It turns true into false and false into true. Now here we can see how that works. That can be built, a truth table can be built in Python Tutor. So we start out with a function that we're going to define called negation of P, and all it's going to do is return not P. Now, not is an operator in Python. It basically does negation to any Boolean. So we're going to be inputting P, a Boolean, into our negation function, and then return not P. And then this bit from lines 4 through 7, that's going to print out a truth table. So there is going to be one of these for each one of our operators, and I'm not going to go through all of them, but I'm going to do some of them, and I encourage you to do the other ones yourself. But let's just step through this one. So first we're going to, the red arrow is here, so it's going to read this and not do anything other than just define this function over here. Now we're going to print P and A right there. Next line says, for P in the list true, false. The reason we're doing that is because those are all the possible truth values of P. It's true or false. And for each one of them, we're going to define A to be the negation of P, so the negation of true or the negation of false, and then we're going to print out P and A. So when P takes on the value of true, A will be assigned whatever the output of this function is, which is going to be false. So there's A assigned false, and then we're going to print P and A. So true, false. Notice that is this second row of our truth table. True, false. Next, when P is false, A will be assigned to the negation of P, that is, the function runs, and A is now assigned false, and then, A is now going to be assigned false because that's what the output of the function is going to be. And then we print out false, true. I misspoke. A is assigned true because it negates it. So because I muddled that, I would encourage you to work through this and see how all that works. We'll do a couple others. Next is conjunction. And as I said before, a conjunction is just combining two propositions with and. So now look at the truth table. Now we have a P basic proposition and a Q basic proposition. And we have all the combinations of P and Q. So we have true, 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 false, false, true, false, false. And we said before in the other video that P and Q, the conjunction, is true whenever P and Q are true. It's false otherwise. So look at this. When I have P true, Q true, then the conjunction is true, and in every other case is false. Okay? Now what it would be a good idea is for you to write down all these basic truth tables, which are also listed on your notes, and have these handy somewhere together so that when you're doing the other truth table problems, you can refer back to them. So let's walk through the Python tutor for the conjunction. So we're going to start out by defining a function called conjunction for two Boolean inputs, P and Q, and just return P and Q. And is a operator in Python. So the function has been defined. Now we're going to print P, Q, and A. P, Q, and A for P, Q, and then the conjunction. And then for P in true and false, and Q in true or false. Now notice we have two different for loops going on here because P can take on the values true and false, and so can Q. So we start out with P, Q, and Q true, and we define A to be the returned value of the conjunction function for the given values of P and Q. So we run the function where P is true and Q is true. So the function is going to run. Its returned value is going to be true. So that's what A will be assigned. A will be assigned true. And now we print out P, Q, A. True, true, true. And that matches this row of our truth table. Now we go back up to line 6 because we're inside this second for loop. And now Q is going to take on the value false because we cycle through true and false, all the values in this list. Now we're going to run the function again, but this time the function is going to run with P true and Q false. And it's going to return a false because remember, an and is only true when both are true. A was assigned false, and that line is now printed in our table. So if we skip to the end, we can see this full truth table for the conjunction. Now, I would encourage you to go through these Python tutor exercises, or examples rather, for all of the rest of them. But for the sake of time, I'm not going to. Now, here we have the truth table for a disjunction. We have our P's, our Q's, and then P or Q. And we said before that P or Q is true when at least one of P and Q are true, false otherwise. So I have true, true, the disjunction is true, true, false, true, false, true, true, false, false, false. Here's the one for the exclusive disjunction. True XOR true is false, because remember, the exclusive OR is true only when one of P and Q are true, false otherwise. So true, false is true, false, true is true, false, false is false. Here is the if-then, or the implication. We said before that this is only going to be true, only going to be false when P is true and Q is false. So look, this is the only row where we have a false for the implication. So true implies true is true, true implies false is false, false implies true is true, false implies false is true. Now I'm going to come back and talk about this in just a few minutes about why this is the case, because it can trip people up. But for now, you can just kind of memorize it, and then we'll think about intuitively why it makes sense a little bit later. And I want to come back to this stuff, and I want to look at by implication. This is the if and only if. We said an if and only if is true when P and Q have the same truth values. So P if and only, true if and only if true is true, true if and only if false is false, false if and only if true is false, and false if and only if false is true. The by implication is like an implication going in both directions. So think about the arrow going from P to Q. When I have true implies false, that's going to be false. Now think about the arrow going from Q to P. Here I have true implies false. Well, that's also a false. That's why this truth table looks the way that it does. All right, let's go ahead and jump into the handouts. A lot of this is just condensed from the textbook, but we have the truth tables in closer together form. Here is the truth table for the negation. Here are the truth tables for the conjunction and the disjunction, both together. Here are the truth tables for the exclusive OR, the implication, and the by implication. Okay, so we have all these truth tables here that you can look at. All right. Here is an example that you can practice, and I encourage you to watch this video. This video has some examples of doing truth tables. And the last thing I want to talk about is called logical equivalence. So two propositions are logically equivalent if they have the same truth tables. So this proposition, not P and Q, the proposition not P or not Q, they're logically equivalent. Because if you do their truth tables, this column and this column are exactly the same. So they're logically equivalent. Now, this equivalence is an example of something called DeMorgan's law. DeMorgan's law, it tells us a way to distribute a negation over a conjunction or a disjunction. And here's an example you can watch of logical equivalent statements. Please watch that example video. But DeMorgan's law says this: if you negate a conjunction, you negate the two propositions and you flip. You flip it from a conjunction to a disjunction. And if you negate a disjunction, you negate the two propositions and you flip it from a disjunction to a conjunction. So those are logically equivalent statements. And DeMorgan's law is an important thing to be familiar with. And we're going to see some more types of DeMorgan's laws later on. So what I would like to do now is, number one, encourage you to work every one of these problems. And I'm going to do a couple from number one. All right, so here's the number one from the practice. I'm going to do part A and part D. So notice that part A has two basic propositions, a P and a Q. So whenever you make one of these truth tables, you start out with your basic propositions. Mine are P and Q, and you're always going to have 2 to the power of how many propositions there are rows. So that means I'm going to have 4 rows, because I have true, 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 false, false, true, and false, false. Those are the rows that I have. Now what you do is you start putting things together, looking at your most basic terms, building up to the full thing, to the full compound proposition. So I have a negation of Q, so I'm going to put not Q, a column for that. Next, I'm going to add a column for P or not Q. And then I'm going to have a column for P or not Q implies Q. And then I just fill in my table using what I know about those basic truth tables. So first of all, I have a negation, not Q. So I'll look at the truth values in the column for Q and I just flip them. So true becomes false, false becomes true, true becomes false, false becomes true. Now I have a disjunction, and I'm looking at the disjunction between this column and this column. So true or false is true, true or true is true, false or false, well, that's going to be false, and false or true, that will be true. Finally, I have an implication going from this column to this column. So I'll look at this one implies this one. So I have true implies true is true, true implies false is false, false implies true is true, and true implies false is false. So this last column right here is the truth table for this entire compound proposition. That is, this proposition is only true. This proposition is only going to be true when P and Q are both true, or when P is false and Q is true, because that's when the whole thing works out to be true from the truth table. Now let's see if we can work on part D. Now, once again, we only have 2 basic propositions here. So we're only going to have a column for P and a column for Q. And that means we're going to have 4 4 of these rows. There's row 1, row 2, row 3, and row 4. Now, putting this together, we're going to start from smallest compound propositions to largest. So I do see a not Q in there. So I'm going to have a not Q. Next, I have P if and only if Q. So P if and only if Q. I also have a P if and only if not Q. P if and only if not Q. And finally, I have the exclusive or between those two if and only if statements. So I have P if and only if Q, exclusive or P if and only if not Q. So again, you just work from right to left, filling everything in, and that's how you do the truth table. All the combinations for P and Q are going to be true, 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 false, false, true, false, false. Now do the next column. True becomes false, false becomes true, true becomes false, false becomes true. Now I have an if and only if. Remember, the if and only if is true only when the two parts of it have the same truth value. So true if and only if true is true. Here I have they're different, so this will be false. Here they're different, so false. And false if and only if false, that is true. Here I have P if and only if not Q. So in this case, I'm looking at this column and this column and comparing those two together. So that's going to give me true if and only if false. Well, that's false. True if and only if true is true. False if and only if false is true. False if and only if true, well, that's false. Okay. Finally, I'm going to take these two columns and I'm going to do an exclusive OR on those. Remember, the exclusive OR is true when exactly one part is true. So true, exclusive OR false, that's true. False XOR true is true. False XOR true is true. And true XOR false, well, that's also true. So it turns out that this statement right here that we were interested in is always true. Something that is always true is called a tautology. Something that is always false is called a contradiction. Now, I said I was only going to do A and D, and I am, but I do want to look at C and talk about how you would set that up. Notice that there is a P, a Q, and an R in there. So for P, Q, and R, there are 3 basic propositions, which means you have to have 2 to the 3rd or 8 columns to start out to get all the different combinations of true and false. And that would be true, 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 false, true, true, false, 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 true, true, false, false, true, and false, false, false. So if you're ever doing a problem that has 3 basic propositions, that's how you would start it out, and then you would just finish the problem the way that you did for the other 2 examples I did. Again, watch those example videos from the online notes for more illustrations of doing truth tables. I'm going to do one more thing though before I talk about the implication and why it works the way it does, and that's just to illustrate how to show 2 statements are logically equivalent. All right, so I have, for this particular problem, 2 propositions or statements. I have P implies Q and not P or Q. So if you want to show things are logically equivalent, you show they have the same truth table. So what I'm going to do is I'm going to take all the basic propositions I have, which are P and Q in this case. So I have P and Q. So that would be true, 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 false, false, true, false, false. And I'm going to do the same thing as I did before, but I'm just going to do everything all on one truth table. So first of all, I have P implies Q. That's going to take care of this one. And then I'm going to start working my way up to this one, Well, this one is also pretty basic. I have a not P, and then I have a not P or Q. Now, just to illustrate a point, I'm also going to put another one in here, and that is P implies Q if and only if not P or Q. So let's work out this truth table. So P implies Q. This is just the truth table for an implication. So true implies true is true. True implies false is false. False implies true is true. False implies false is true. Not P, well, I take everything in P and I flip it. So this will be false, false, true, true. And then not P or Q, I look at not P and Q and do this junction. So false or true is true. False or false is false. True or true is true. True or false is true. Now, I want you to notice something here. Notice that this, whoops, not that one. Notice that this column and this column have the same truth table. That means they are logically equivalent. Another way to see that is to look at what happens when you do the bi-implication of those two statements. True if and only if true is true. False if and only if false is true. True if and only if true is true. And true if and only if true is true. Okay? So another way to say that two propositions are logically equivalent is that the bi-implication between them is a tautology. Okay, that's another way to look at logical equivalence. I want to consider the implication statement, the if-then statement. So let P be the proposition that it is raining, and let Q be the proposition I have an umbrella, and let's consider this compound proposition, if P then Q. That is, if it is raining, then I have an umbrella. So I want us to think about all of the different situations for P and Q, when they're true and when they're false. So I could have both of them true. I could have P true and Q false, P false and Q true, or I could have both of them false. Okay? So consider these and consider this statement in English. Okay? So if P is Q and Q is true, that means you see me. that means it is raining. And I have an umbrella. That's the situation. You see that it is raining and I do have an umbrella. So what that means is I am not a liar. That is, I did not tell you a lie when I said if P then Q. You see that it is raining and you see that I have an umbrella. I am not a liar. Now, let's consider a different situation. Okay? Consider the situation where it is raining and I do not have an umbrella. So the promise that I made was that whenever it is raining, I would have an umbrella. But you see me somewhere and it's raining and I don't have an umbrella. In this case, I am a liar. I lied to you. I broke my promise that if it is raining, then I would have an umbrella. Now, the next situation I want us to think about, it's not raining because P is false. It's not raining and I have an umbrella. Maybe I want to keep the sun off of me. Maybe I had the umbrella at my office and I'm just carrying it home. But for the purposes of what we're doing here, the only thing that I promised you is if you see it raining, then I'm going to have an umbrella with me. If it's not raining, then my promise doesn't even come into play. It doesn't matter what I said to you because it isn't raining. The only condition that I said anything about my promise would be if it's raining. So if it's not raining and I have an umbrella, I'm still not a liar because my promise only mattered if it was raining. Similarly, for the last situation, it's not raining, and I do not have an umbrella. That is, it's sunny outside and I don't need an umbrella, so I don't have an umbrella. Well, in this case again, for the same reasons as before, I'm not a liar because my promise only comes into play when it is raining. Well, that's why the truth table for an implication works the way it does. If I'm not a liar, then I'm telling the truth. If I am a liar, then I'm saying something false. That's why the truth table for an implication is true, false, true, true. So whenever you're thinking about this, just think about, are you being told a lie or not? And this is a nice intuitive way to understand what's going on here. All right, that is all that I wanted to say for this section. There will be another video or videos next week going over the next sections in logic. If you have any questions, let me know, and I will talk to you all later.